Okay, so now we're going to take a look at the third example here. So our parent function on this one is y equals 6 to the x. So our x values we're going to start with are -1, 0, and 1, which means we're going to get y values of 1/6, 1, and 6. All right, looking back to the equation, there's no right or left transformation, so we don't need to do anything on the x side. All right, on the y side, though, we've got a times 0.1 and a -3. All right, so if I go through this, we'll do that work off to the side. I've got 1/6 times 0.1, which is 1/10, right, -3. That's 1/60th minus 3. So that's like -2 and 59/60ths. All right, we could definitely use a calculator to get the decimal for that. The key to recognize is it's really close to -3. Right, but we're -2 and 59/60ths. Now, if I plug 1 in, it's a little nicer number because we've got 1 times 0.1, which is 0.1, right, -3, which is -2.9. Then I go to 6. 6 times 0.1 is 0.6. 0.6 minus 3 is -2.4. All right, that gives me enough to plot my points. So I've got -1 and really close to -3. All right. Then we've got 0 and 2.9. So again, pretty darn close to -3. And then we've got 1 and -2.4. So that jumped up a little bit more. All right. The whole thing was shifted down 3. So I know my horizontal asymptote is here at -3. And then the base was bigger than 1. So I know this is exponential growth. That's going to be enough for me to get a close enough graph for what we need. So again, I'm going to carry that information over. The asymptote is at y equals -3. The domain is -infinity to infinity. The range starts at that asymptote, so -3, but doesn't touch it, and continues up forever to infinity. All right, this one is a clear growth. We're back to a more friendly growth decay question compared to the last one. As far as the transformations, we've got a vertical stretch by a factor of 0.1. Right, so that's really a compression, right? Because it's kind of squeezes it down. It makes it a little shallower, right? And then a shift down of -3. So we're shifting down 3 units, right? And that takes us through that graph. Now, in the next videos, I'm going to look at a couple applications, and they really focus in on exponential growth or decay when you're talking about one increase per time period. Right, so this isn't a continuous growth. We'll talk about that tomorrow. It isn't a compounding growth. We'll talk about that tomorrow as well. This is if we strictly have 1% increase for each of the time periods as we go through. All right, and there's two basic models for that. There's a growth model, right, where we have this model, right, and that 1 plus r is called the growth factor. R is the rate it grows at, right? And then for decay, we have this one, and the 1 minus r is the decay factor, right? And again, just the r is the rate at which it's decay. So let's look at this first example here. We've got the initial number of bacteria in a culture is 12,000. The culture doubles each day, right? Write an equation to model the population Y of the bacteria after X days. All right, so the first thing we're going to do is A is the initial amount. So I have Y equals 12,000, right? Because that was our initial amount in the culture, right? Then it says it doubles each day, right? That means every single day we're having 100% increase, right? So my R is 100%, but then we have to shift that from percents to just a regular number. So it's really 1.00. All right, so I get parentheses, 1 plus 1 raised to the t. Now I'm going to clean that up. Y equals 12,000 times 2 to the t. Right? Now, if I look to graph this, basically we're getting it doubling every time. So I'm going to start with an initial amount here at time 0 of 12,000. All right, then at time 1, I'm going to jump up to 24,000. All right, because that's one doubling. When I go to 2, it's going to double again. So it's not just going to take one step. It's going to take double that last step. So I'm at 48,000. right? And then it'll keep doubling like that, and that's where we get that exponential super fast growth coming from, right? So that would be a rough sketch of the important part of this graph, right? There would be more graph on the negative side, but we're not going to concern ourselves because we had kind of that initial condition and we're moving forward. This says, what does the y-intercept of the graph represent? That represents our initial amount. All right, so that's the starting amount that we have. Now, if we look at 5 here, 5 says the first U.S. Census was conducted in 1790. At that time, the population was 3.9 million. Since then, the U.S. population has grown by approximately 2.03% annually. Write an equation to model the situation. Approximately, what was the population in 1843? Right. So there's two parts of this question. So first thing we're going to do is we're going to establish an equivalence. We're going to say t equals 0, right, is equivalent to 1790. All right, that's going to give us kind of a starting point so we can start this function without doing a horizontal shift, right or left. All right, so we have that. We know the initial population at that time up here, 3.9 million. So I've got y equals 3929214 times 1 plus, and then it said there was a growth rate. The growth rate was 2.03%. So I'm going to shift that 2 decimal places so that we're looking at the equivalent like number for that percent. So 0.0203, and that's going to be raised to the number of years t. All right, so this is our exponential growth model that we're going to use for this situation. Now it said once you have that, approximate the population in 1843. So we need to find the number of years since 1790. So I'm going to do a quick subtraction here. I've got 1843 minus 1790, right? We can bring the 3 down, cancel that 8 to a 7, 14, that's a 5. And so we're looking at 53 years. Now, you're welcome to do that in your head. I just wanted to show it so that everybody could see it there. And we're going to take that and plug that in. So we've got y equals 3, 929, 214 times 1.0203 raised to the 53rd power. Now, at this point, I'm going to leave it to you to take that to your calculator and get an approximate value for that. And that's how we'd use the model that we wrote for that particular problem. In the final one here, this one shifts, says depreciates. Right? Depreciates means it loses values. This is something when you start doing your own taxes, and if you own a business, you might buy something for the business and you're able to depreciate it over time and basically write off a certain portion of the value that's lost because it's getting older and eventually will have to be replaced. So if we look at this, it says it depreciates at 10% per year. All right, so right there, they're giving you the R value. R value is 0.10. All right, again, it's 10%, so we shift 2 decimal places, and that's where we're getting that 0.1 from. How much would a new $15,000 mower be worth after 5 years? So we're going to write our decay model. Y equals 15,000 times 1 minus 0.1 to the t. That's the standard model. If I clean that up, y equals 15,000 times 0.9 to the t. Right? They asked me the specific question, what's the value after 5 years? So I'm going to drop 5 in, and I get 15,000 times 0.9 to the 5. Right? And this is, again, where we go to a calculator, and I'm going to leave that part for you, and we'll plug that in and get an approximate value for that. That would be the estimated value of that piece of equipment after the 5 years. All right, now part B says estimate, use a calculator when the mower will be worth about $2,000, round your decimal to round to 2 decimal places. All right, so this is a place we're going to use the graphing calculator, and we're going to have to look for an intersection between the model that we built, 15,000 times 0.9 to the t, and again, you can enter that on your calculator as an x, and the line 2,000. Right, that's going to allow us to find the intersection of those, which will give you the t value that makes that happen. Right now, we don't have an algebraic means to solve that. Later in the chapter, we will. All right, I hope that helps with the notes today and get you a good start on the homework. I should be back on Monday and able to take any questions and get us through the next section. Bye.